This recording is for the 7-4 lesson, Similarity in Right Triangles. We have a theorem here and a couple of corollaries to it, and then we're going to work through some practice problems on geometric mean, which is effectively what this lesson is about. So theorem 7.3 says if you draw an altitude from the right angle to the hypotenuse of a right triangle, you create three similar triangles. The first one being the original big triangle, and the other two being the two triangles that are created when you draw that altitude. So this is theorem 7.3. Triangle FGH is a right triangle with right angle FGH, or angle G, and the altitude of the hypotenuse is JG, right here. Remember, an altitude goes from a right angle, or from a vertex to a right angle. So from vertex G to right angle J. Alright, so the two triangles formed by the altitude are similar to each other and similar to the original triangle. So triangle FGH, and I'm looking at this statement right here. Triangle FGH is similar to triangle FJG, which is similar to triangle GJH. So there are two corollaries to that theorem that relate the parts of the triangles formed by the altitude of the hypotenuse to each other by their geometric mean. The geometric mean, which is, that's what x is here in this proportion. The geometric mean x of any two positive numbers a and b can be found by this proportion. So basically, when you're using a proportion to find geometric mean, whatever is standing for geometric mean, whatever variable, x, y, whatever, is going to go in the extremes position, and the two numbers that you're finding the geometric mean of go in the means positions. So this says, what is the geometric mean of 8 and 12? So notice that 8 and 12 are in the numerator of one fraction and the denominator of the other, and the geometric mean itself is represented by the x's. So when you cross multiply here, x times x is x squared, and 8 times 12 is 96. To undo the square, you have to take the square root of both sides. The square root of a square just basically cancels out the square root and the square, and you have x. And you have the square root of 96 here. So going from 96 to 4 root 6 is a process that I thought needed a little bit more explanation. This is called simplifying your radicals. Simplifying radicals, I've shown the process over here on the right. If you start with the square root of 96, you're going to make a factor tree of 96. Since it's an even number, I just started by dividing it by 2. So 96 is 2 times 48. And any number that's not prime, you're going to continue factoring from that. 2 is already prime, so I underlined it. 48 is 2 times 24. 2 is prime, 24 is not. 24 is 2 times 12. 2 is prime, 12 is not. 12 is 2 times 6. 2 is prime, 6 is not. And 6 is 2 times 3, both of which are prime. So basically, my prime factorization of 96 is 2 times 2 times 2 times 2 times 2 times 3. So from this point, I circled any pairs I have. I have a pair of 2's here. I have another pair of 2's here, and then I have an extra 2 and a 3. So think of it this way. If you have a pair, they get to go on a date and leave the house. So this pair of 2's went on a date. One date. So there's the 2 that represents that dating pair. And this pair of 2's also gets to go on a date. The dates that are outside the house get multiplied together, so 2 times 2 is 4. And the numbers that do not have a date have to stay home. So the 2 and the 3 get multiplied together back in the house or under the square root sign or radical sign, and you get 6. So 4 root 6 is the simplified radical version of root 96. And we will practice this with the practice problems in this lesson so you can see it over and over again. Okay, corollary 1 to theorem 7.3. The altitude of the hypotenuse of a right triangle divides the hypotenuse into two segments. So those two segments here are AD and BD. The length of the altitude is the geometric mean of those segments. So CD is the geometric mean of AD and DB. So you see that they have put that in a proportion here. Since CD is the altitude of right triangle ABC, it is the geometric mean of the segments of the hypotenuse AD and DB. Okay? So this may make more sense when we put some numbers to it, hopefully. Oops, sorry. All right, corollary 2 to theorem 7.3. The altitude of the hypotenuse of a right triangle divides the hypotenuse into two segments. The length of each leg of the original right triangle is the geometric mean of the length of the entire hypotenuse and the segment of the hypotenuse closest to it, or adjacent to that leg. So basically, 8 is the geometric mean of 4 plus x and 4. So you can see that they've laid that out here in a proportion. The adjacent leg, which is 8, is the geometric mean between the segment of the hypotenuse closest to it, which is 4, and the entire hypotenuse, which is 4 plus x here. So to solve it, they just cross multiply. 8 times 8, of course, is 64. Remember, anytime that you have the a binomial in a proportion, you need to put parentheses around it to keep it together so it doesn't get away. So that when you're cross multiplying here, 4 times the quantity 4 plus x is represented here. Remember, when you're distributing, you have to distribute to both parts of the inside the parentheses. 4 times 4 is 16, and 4 times x is 4x. So the next step here then was to subtract 16 from both sides, and this is all written over here, but I wanted to make sure that you could see it in practice here. So 16 times 6, or minus 16 goes away, bring the 4x down, and 64 minus, and I put 16 there, I'm sorry. Okay, 64 minus 16 equals 48. And then we simply divided both sides by 4, and 48 divided by 4 is 12. So that tells us that x equals 12, so which means this is 12, which means the entire hypotenuse here is 16, if they were looking for that. Okay? All right. So in our exercises here, we're going to start by writing a similarity statement relating the three triangles in the diagram. So this is exactly what was done up here in this first theorem. This is the similarity statement that was comparing these three triangles. All right, so we're going to do the same thing down here. Okay, starting with triangle. You can put a triangle symbol here. Triangle ONP is similar to, remember that similar symbol is just a single squiggle. Okay, so ONP was the bigger triangle there. I'm going to color code these just so you can see. All right, ONP was the bigger one, and it's already in black. So I'm going to switch my color here to red. Okay, I'm going to say to triangle, and I'm going to talk about the smallest triangle here. But I need to make sure that I put the corresponding letters in the right positions. For instance, ONP, N was the right angle, and it's the middle letter here. T is the right angle on this one, so it's going to be the middle letter on this one. So how do we know where the N and the O go? Well, if you turn this triangle around so that it looked like just a shrunken version of ONP, then you would see that the N in the red triangle matched up with the P in the big triangle. So N goes here, and O goes here. So ONP is similar to triangle OTN, which is similar to, let's change colors again. We'll blue this time. So now we're going to be talking about this triangle. Okay. And again, we're going to want the right angle in the same position as the original. In the original triangle, N is the right angle. In the red triangle, T is the right angle. And T is the right angle in the blue triangle also. So that's going to go in the middle of this statement. Okay. So triangle ONP is similar to triangle NTP in this situation. NTP. All right. So we're going to do the same thing on each one of the, well, on number 2 also. Sorry, getting ahead of myself here. Okay. So on this one, our original triangle here is triangle FHG. Triangle FHG. Okay, is similar to. So we can go ahead and switch over to the red for our smaller triangle here. See my smaller triangle right here, and I know that M is that right angle. M is the right angle in the little triangle here, so it's going to go in the same place as H, which is the right angle of the bigger triangle. So M will be in the middle. M will be in the middle. Okay. So in the bigger triangle, FHG, G was that smaller angle that extended far out. And in this little red triangle, H is the small angle that extends far out. So it's going to be in the same position as that G. So the F will go first then. Triangle FMH. All right, and then that's going to be similar to, switching over to blue. Okay, triangle. And we're looking at this one now. Okay, so M, again, is going to go in the middle. Okay, and in my original one, FHG, the extended skinnier angle was G, and it is in this blue one also, so the G is going to go here. So we have HMG. All right, there you go on that. Okay, so 3, 4, 5, and 6 are using two numbers to find the geometric mean, which is exactly what this example up here is. What is the geometric mean between 8 and 12? Basically, you just multiply those numbers together and take the square root, okay? So if I was going to set this up in an equation, I would say 2 over x equals x over 8. Okay? Then what I would need to do there is cross multiply. X times x is x squared, and 2 times 8 is 16. So then x is the square root of 16, which of course is just 4. Technically it's positive or negative 4. Okay, so there's for number 3. All right, switching colors again, make sure we don't get everything mixed up here. Okay, so for 4 and 6, again, if we were going to set this up, we would say 4 over x equals x over 6. Okay, so when we work this one out, we would have x squared equals 6 times 4, which is 24, which means x is the square root of 24. We do need to reduce that, though, reduce that radical. So I'm going to kind of do that off to the side here. If I'm starting with the square root of 24, and I want to break that down in a factor tree, I know it's even, so I'm going to start by dividing it by 2. So 24 is 12 times 2. 2 is prime. I'm going to underline it and leave it alone. 12, also an even number, is 2 times 6. Again, 2 is prime. I'm going to leave it alone, but 6 is not. So I'm going to break it down even further to 3 and 2. 3 times 2, both of which are prime. So now I have my prime factorization of 24. 2 times 2 times 2 times 3. I have a pair of 2's here. And then I have a spare 2 and a spare 3. The 2 and the 3 down here don't have dates, so they have to stay home. This pair of 2's gets to go on a date, so it's going to come outside the bracket. It's going to come outside the radical. So there's the 2 that is the date. And then this 2 and 3 stay home. 2 times 3 is 6. So for 4, the geometric mean of 4 and 6 is 2 root 6. Okay. I do know that some of you have never seen this process before. Most of you probably never seen this process before, but we'll practice it some more in class. So 8 and 10, the geometric mean between 8 and 10. Of course, we started off 8 over x equals x over 10. X over 10. So when you cross multiply here, x squared equals 80. Okay. So x is root 80, and of course we need to simplify that. And we'll do that off to the side. Try not to run out of space here. Square root of 80. 2 times 40. 2 is prime. 40 is 2 times 20. 2 is prime. 20 is 2 times 10. 2 is prime. And 10 is 2 times 5, both of which are prime. All right, I'm going to circle my dates. I have a pair of 2's here that's going to go on a date. And I have another pair of 2's here that's going to go on a date. So the only one who has to stay home because he doesn't have a date is this 5. Okay? So root 80 is going to simplify to 2 times 2. You have a date here that comes out as a 2. You have a date here that comes out as a 2. So 2 times 2 is 4. And you have root 5 because he doesn't have a date. Sorry, 5. All right. Okay, I'm going to squeeze one more in here. Let's find a color for him. How about purple? Okay. 25 and 4. So let's do a little bit of... cut out a couple of steps here. Every time we have found the geometric mean between two numbers, we've basically just taken the square root of the product. So square root of 24, square root of 16. So the square root of 25 times 4. If you think of 25 as a quarter, as money. 4/4 is $1. So the 25 times 4 is 100. No, I guess we'll go ahead and write this out. 25 over x equals x over 4. So x squared equals 100. So x equals the square root of 100, which is 10. I hope y'all knew that one. There we go. Look at that. I squeezed it all in there. All right. So this is one of those situations where I really hope that you are watching and listening to the video and not just trying to copy notes down, because you can see that there's a lot of work here all over the place. So if you're listening, then you know what goes with what. Okay, so 7, 8, 9, and 10, this is use the figure to complete each proportion. So I and K, this is I down here, and it's kind of hard to see, so I'm going to kind of draw over that a little bit more clear, I hope. Let's see if I can make this a little bit more clear. This is I, and that's J. Okay. All right, so this is I and K. What is the geometric mean between I and K? So it tells you F here. F is one of the legs of the big original right triangle. Remember that that is the geometric mean between the entire hypotenuse and the piece closest to it, which are I and K. So yes, F is the geometric mean between I and K. So F would go right there. 8 is showing J as the geometric mean. Okay, so the geometric mean is going to be in the bottom one and top of the other. So when you have the same thing in the bottom of one and top of the other, that is the geometric mean. Okay, and we should type this out too. So J is the geometric mean between I, well this, J is the altitude. And remember, the altitude is the geometric mean between the pieces of the hypotenuse that it creates, or I and H. Okay. And then on 9, this is showing F again. F is the geometric mean between, and this is the same as number 7. F is the geometric mean between I and K. And K. Okay. All right. So I'm going to type that out a little bit just so that you understand what these things are saying. Hopefully this will help. F is the geometric mean between I and K. And over here, J is the geometric mean between I and H. And then 9 is basically saying the exact same thing as number 7, so I don't need to type that again. All right, on 10, error analysis. A classmate writes, this proportion, this is showing 5, which is the altitude, and we know the altitude is the geometric mean between the pieces. So 5 would actually be the geometric mean between 3 and B. This is showing 5 is the geometric mean between 3 and 3 plus B. Okay, so we need to explain this a little bit better. Okay, so 5 is the altitude, so it is the geometric mean between 3 and B. And that would look like this. Go ahead and write this out for you. The correct version of this would say 3 over 5 equals 5 over B. That would be correct. Okay? If there was another variable here, let's say this was A. Okay? If we were going to use 3 and 3 plus B, then we would say that, let's see, if we called the shorter leg of the original triangle A, then A is the geometric mean between 3 and 3 plus B. Okay? Because the legs are the geometric mean between the entire hypotenuse and the piece closest to it. So that correct proportion would look like this. 3 over A equals A over 3 plus B. Alright, I hope this has been somewhat enlightening. Please watch it again if you missed something, or watch the second video. There's going to be a second video on the Canvas page also. So please give them a watch and allow yourself to the best possible chance of learning this content. And then do the practice, because that's your homework grade. Thank you.